Okay, folks, good evening. I'm delighted to be here, and I thank you very much for the invitation to speak to you this evening. I want to thank Jim Matheson for setting it up and Andy last night for help with the logistics. And I'm just glad to have all of you here. So I'm going to organize the talk in the following way. I'm first going to show you a little video of what actually happened on September 14th, 2015. Then I'm going to give you a short overview of cosmology as we look at it today. And then I'm going to talk a little bit about stars and how we think about them and how it is that black holes emerge from stars. Then, of course, I have to tell you what a black hole actually is, so I will do that. And then what gravitational waves are, and then what the LIGO instrument is able to do. So without further ado, let's start.
From the dawn of our species, what we know of the universe has come from what we could see, from light. Visible light for the first stargazers, ultraviolet and infrared light for the Hubble Space Telescope, microwaves and radio waves blasting from the cores of galaxies. But there are other vibrations we can't see. 100 years ago, Albert Einstein proposed his theory of general relativity. He predicted that the acceleration of massive objects would roil the fabric of space and time, sending out gravitational waves. Nobody had detected one until now. A billion years ago, in a distant galaxy, a pair of black holes circled each other. They spiraled inward and finally merged. The collision unleashed the energy of 1 billion trillion suns in a fraction of a second. That energy is still spreading outward in the form of gravitational waves, space-time distortions rippling across the universe at the speed of light. As a gravitational wave travels, it compresses space in one direction and stretches space in the other, like sound going sideways. This push and pull weakens with distance. The wave fades to a whisper, so faint that physicists long thought that gravitational waves would never be measured on Earth. But in Louisiana and Washington, two of the most sensitive detectors ever built have been waiting and listening. Astronomy has grown ears. This is LIGO, the Laser Interferometer Gravitational-Wave Observatory. Each detector has an L-shaped antenna with arms 2.5 miles long. Inside the ends of each arm, mirrors of ultra-pure glass are isolated from the noise, heat, and vibrations of the outside world. A beam of laser light measures the separation of the mirrors. The beam is split and sent toward mirrors at the end of each arm. If the arms are precisely the same length, the returning beams cancel each other out, and LIGO's detector sees no light. But a passing gravitational wave would stretch one arm and squeeze the other. The resulting discrepancy is tiny, a fraction of the width of a proton, but enough to misalign the beams and light up the detector in a rhythmic pattern. On the 14th of September 2015, LIGO detected a flickering light and turned it into a sound wave. A chirp. It was the echo of the marriage of those two black holes, a cosmic cataclysm that happened 1 billion years ago. Hearing a gravitational wave has opened up a new kind of astronomy. For the first time, we have ears as well as eyes on the heavens. And LIGO is only the beginning.
So that was a piece from Dennis Overby in the New York Times right after the press announcement in January of 2016. So now I'd like to talk a little bit about the way we look at cosmology these days and the way it's developed, particularly over the last 100 years. It's been a fantastic outpouring of new ideas. So let's start with talking about something that I hope all of you have had the opportunity to see, namely the Milky Way on a beautiful moonless night with no clouds and far away from the city. You see the most wonderful display up in the sky, a picture of which is on the right. So the Milky Way is a spiral galaxy. It's about 100,000 light years across, and it contains at least 100 billion stars. Now, a light year is an enormous distance. It's 16 million miles. So that gives you some idea of the dimensions that we're talking about. And this is only a tiny fraction of the universe. Now, it turns out that there is even though we don't know what a black hole is yet, there is a huge black hole called Sagittarius A star that's sitting at the center of our galaxy. It contains, we think, about 4 million solar masses. That's what this symbol here stands for, a solar mass, and LY stands for light year. So there's a 4 million mass black hole at the center of our galaxy, and Earth is about 26,000 light years away. So if the black hole is, say, here, we're down here somewhere. Now, until about 1920, all matter in the universe was thought to reside within the Milky Way. That's mostly because astronomy until about that time had very poor ways of measuring distance. So you had a hard time to telling how far away objects were in the sky. So it sort of looked like everything was kind of piled on top of one another. You couldn't see the distinctions looking outward. Now, the universe looked at that way appeared to be static, unmoving, unchanging. Isaac Newton thought so, and he was an intellectual giant of the 17th century, so his opinion mattered a lot. But little did we know what was really going on out there. So starting in about 1915, I want to talk about a revolution that lasted about 100 years, still going on today. First, Albert Einstein published his theory of general relativity in 1915. We'll talk a little bit more about it in a few minutes. This theory is today the backbone of our entire understanding of cosmology. It revolutionized everything. Then in 1924, Edwin Hubble was the first person to realize, to measure, to see that there were galaxies outside the Milky Way. And he could do that because it was possible then to measure distance to some of these galaxies. And he could see that they were far enough away to be outside the Milky Way. Then in 1929, Hubble was quite a guy. And he discovered in 1929 that not only were there's these galaxies out there, but they were all receding from us and receding from each other. So this meant that the universe is expanding. And that was as incredible an idea today as it was back then. People just could hardly understand what that meant. Now, if things are expanding in that way, it doesn't take you long to realize that there must be an origin of that expansion somewhere. And that's where the idea of the Big Bang got started. All these galaxies came from some originating event back at the beginning of time. This idea was really first proposed by a Catholic, a Belgian Catholic priest named Lemaitre, and he first did this in 1930 and was quite a proponent of it, a very prominent contributor to these ideas. Then, on a somewhat parallel track, an astronomer named Fritz Zwicky was studying these objects, these galaxies, studying their rotational motion. And he realized that they were spinning faster than they should if they had only the matter that you could see. In other words, he proposed that there had to be something dark inside these galaxies that added to the mass of the galaxy that allowed it to spin more rapidly. So that was the origin of what we today call dark matter. And not ironically, but interestingly enough, we know really no more about it today than we knew about it back then, which is almost nothing. We know it's there, we don't know, and we know it's dark, and we know it attracts, we know it has a gravitational force associated with it, but we don't know anything else about it. Then in 1964, a measurement was made of something called the cosmic microwave background radiation. I'll tell you about it in just a second, but it's important because it's a signature that the explosion at the time of the Big Bang really occurred. It's a direct measurement of a conclusion that the expansion would require. Then, even more interestingly, if you can top all these things that we've talked about already, in the year 1998, two independent teams discovered through the observation of receding supernovas that not only were these galaxies expanding, but not only was the universe expanding, it was accelerating as it expanded. So somewhere there's a source of energy in the universe that is powering this. And this is called dark energy. And we don't know any more about it than we know about dark matter, which is basically nothing. Then in 2015, gravitational waves were observed, as you just heard Dennis talk about. And so that's 100 years of pretty heady, mind-blowing, mind-changing activities. Cosmology today is nothing like it was back in 1920. Okay, so here is a cartoon that tries to depict what we've just talked about. Down here is the so-called Big Bang. It produced an enormous amount of material, subatomic particles called quarks, and photons, and neutrinos, and electrons. All were produced in this enormous explosion, which lasted a very, very short period of time. And there was an enormous acceleration involved. That's what the curved line here represents, an acceleration of all these particles moving outward. Now, as you may have noticed, when you shake a can of aerosol in your house, it gets colder. That's because an expanding gas will always cool. And this expanding gas also cooled. And as it cooled, the quarks and gluons and electrons coalesced into the particles we know more familiarly, namely protons and neutrons. And of course, there are photons there and there are electrons. So by the time you get here close to this line that's marked 400,000 years, you had moved from a situation where all of these very small subatomic particles had coalesced into particles that we more clearly understand: neutrons, protons, electrons, and photons. And the cooling continued until the protons and the electrons could actually combine to make hydrogen. And then you could actually see through it because there were no more charges lying around. So you could see through this with a microwave receiver, and that's what the cosmic microwave background is. So the cosmic microwave background occurred about 400,000 years after the Big Bang. So the universe continued to cool, and these particles spread all over the place, but in little clumps and voids because nothing is completely smooth. You began to have lumps of hydrogen that would get grower and some voids where there wasn't enough, or wasn't very much rather. And those voids and clumps and so forth grew into the first stars. That's why you see these little white dots here. Then the white dots began to coalesce into solar systems and galaxies. And then more and more galaxies were formed. And then finally, here we are at where we are today, 13.7 billion years after the Big Bang. So this is a very truncated representation of what happened. So now what happens next? Well, we've just heard about the acceleration of the universe. And what people think is going to happen is that the acceleration is going to increase and objects are going to get farther and farther apart from one another, faster and faster, until you get to a point where all matter in the universe really decouples from all other matter. And you end up with a situation that we call the cosmic void. Now, this is billions and billions and billions of years in the future, we think, but that's the idea at the moment. So this is a cartoon that sort of encapsulates all that in one picture. So now I need to tell you a little bit about some of the concepts of space and time that unify all of this. So over here on the right, you recognize Isaac and Albert. And let's talk a little bit about Isaac. So in 1687, he published his famous treatise called Principia Mathematica, which in addition to little trifles like developing the calculus and understanding the fundamental physics of mechanics, he also had ideas about cosmology. In his view of the universe, space and time were completely independent concepts of one another. There's a universal clock for everybody. Everybody measures time the same way. And there's a universal coordinate system for everybody. Everybody knows exactly where they are and where everybody else is. You may think it's strange to say that, but you'll see why I mention it in just a second. In addition, he also, people back at that particular time, thought that the speed of light was infinite. Now, the speed of light is very, very fast, but it's not infinite. But that was not known back then. So that turns out to be an important, very important distinction. Okay, so now along comes Albert, 218 years later. 218 years later. So there's a long time in here where things were basically unchanged. Our understanding of the universe did not change much. But then Albert came along in 1905 and developed special relativity. Now, why is that important? Well, because he said in developing this theory that the speed of light is very fast, but it is finite. And in addition, and this was a stroke of genius, which only somebody like Einstein could think of, I believe. He was incredible in his physical insight. He proposed that not only is the speed of light very fast and finite, but it is the same for everybody who's watching it. Now that may seem a little strange, but let me tell you why it is strange. Let's suppose I'm standing. Let's suppose that I don't know what that is. Somebody's got their microphone on or something. Anyway, let's suppose that I'm standing here and you go by. Sorry. Let's suppose that I'm standing here and you go by me at half the speed of light. And the two of us see another beam of light going past both of us. What Albert said that's so remarkable is that each of us sees that beam of light the same way. We both measure it as going at speed, whatever the speed of light is. We call it c in physics, the speed of light c. So, you know, if this were an escalator in a department store and somebody went by you, you wouldn't calculate his speed that way. You would just add the speeds together and that's what you would get. But according to Albert, that's not what happens. Now, if some of you are interested in knowing how he reached this conclusion, we can talk about it later, but it's a little detailed and not so important right now. Anyway, this notion that the speed of light is the same for all observers forced Albert to introduce the notion of space-time. And that's a concept in which space and time are not independent of each other anymore. They actually are hopelessly intertwined. And if you want to measure any event that happens, you have to take into account space and time and how they're interweaved in order to get the correct answer. So this idea of space-time is important because it's the fundamentals of general relativity, which came next. So it took Einstein 10 years, from 1905 to 1915, to develop his theory of general relativity. I've been studying it myself now. I came to MIT 5 years ago, and when we moved to Boston, and I joined the LIGO group at MIT, and I've been trying to learn general relativity. And all I can tell you is it's hard. So one of the things that it predicts, though, is that space-time is not only, as I described it earlier, an intertwining of space and time, but it's also a curved space. And the closer you are to mass, the more the space is curved. And so that leads to the idea that gravitation occurs not because it's a force by itself, but it occurs because mass warps the space-time surrounding it. So if you come close to the sun, you will follow a different path than you would if you were in flat space, because the sun warps the space around itself. Now, the general theory of general relativity also predicts that the universe will not be static. And this was a direct contradiction of Newton. Now, in one of the amusing sidelights of science, at that particular time in 1915, we had not yet known that Hubble was going to discover in 1924 that galaxies were, 1929 rather, that galaxies were going to be receding from one another, and that the universe was, in fact, expanding. So Albert was in a bit of a panic, and so he monkeyed with his theory and introduced a constant in it that forced his theory to predict a static universe rather than a non-static one. Then when Hubble announced his discoveries, and Albert had to withdraw his constant, which he called the cosmological constant, he said that was his greatest scientific blunder. And all I can say is, I wish I made blunders like that. Now, in addition, general relativity also predicts that gravitational waves should exist, but even Albert thought that they would be too small ever to be seen. And many people agreed with him until pretty recently. Then, in addition, in 1916, a gentleman named Schwarzschild solved Albert's equation, solved general relativity, and predicted the existence of black holes. This was the first solution ever of Einstein's equations. Schwarzschild is an interesting sidelight. He made this discovery while being a soldier in the Austrian army on the front in Russia, in the war, in a foxhole, somehow finding the time to be able to make calculations that I can tell you are really hard. But he did, and he wrote to Einstein, and so it became known who had done this. But sadly, he died not long afterwards from some terrible disease that he got from living in a foxhole on the front in a war. So that's what happened to him. And it's also ironic that he joined the army when he didn't have to, because he was well over 40 years of age, but he wanted to serve his country. Okay, so now let's talk a little bit about some observational details. So this is the Andromeda galaxy. Yeah, I'm showing this one because it's the one that's the closest large one to us. It's 2.5 million light years away. Now, what this means is that, first of all, it's very, very far. But in addition, it means that it takes 2.5 million years for the light from Andromeda to reach Earth. So when you look at Andromeda now, you look at this beautiful thing in the sky, which you can see, by the way, with your naked eye. You're seeing it the way it was 2.5 million years ago. You're not seeing it the way it is now. So this leads to the idea in astronomy that distance in space is look-back time. You tell me that something is 2.5 million light years away, I tell you that the light coming from it is 2.5 million years. So it's important to remember that. Light from the sun takes 8 minutes to reach the Earth. Light from Pluto takes 4.5 hours to reach Earth, and so on. Okay, so right here where I have the little red smiley face, if this were our galaxy, this is roughly where Earth would be. Our solar system would be roughly here. And you can see here the plane of the galaxy. If you try to look through the plane of the galaxy, you're going to have a hard time because there's so much matter there. On the other hand, if you decide you want to look in this direction, you have a much clearer path to what's out here. It looks like there are a lot of stars out here, and there are, but actually space is really quite empty, quite empty. Now, in addition, one of the things that the United States has in terms of its scientific apparatus is something called the Hubble Space Telescope. And it's been up into the space since 1990. And in 1996, I think it was, the director of the Space Telescope Science Institute, a guy named Bob Williams, decided that he was going to take 10 days of Hubble Space Telescope time and just point it out in space, out here along this yellow arrow, just to see what he would see. He didn't expect to see much of anything, but here's what he did see. Oh, sorry, this is the Hubble Space Telescope. I can't go by without showing you that. This is a modest telescope as far as telescopes go, but as they say in real estate, it's location, location, location. And this guy is up in space, above the Earth's atmosphere, and has the clearest view of the heavens you'll ever see. Much better than what you'll see on Earth, except in extreme circumstances. So there it is. It's still going. It's had 5 surface missions So I don't know how much longer they'll keep it operating. Something called the James Webb Space Telescope is supposed to start operating within the next year or two. But it's been a fantastic workhorse, and it's just revealed amazing, amazing things. Anyway, back to Bob Williams. This is what his picture showed. This is a legendary picture now, not only in astronomy, but I think in science in general. This is one of the great photographs ever taken in science. The exposure time was 10 days. It was pointed at the North Star, as I said earlier. The width of this picture is 1/12 the size of the moon. Now, for those of you who think about these things a little more, the moon is about half a degree wide. So it's 1/12 of half a degree. So it's really small. And yet look what's in here. Every object in this picture is a galaxy, except for two. This is a star, and that's a star. But everything else in here is a galaxy. This is a spiral galaxy. This is an elliptical galaxy. This is another spiral. You can see circular, spherical ones down here, elliptical ones here. All of these are galaxies, all of them. Each of these galaxies has hundreds of billions of stars. And we think today, we estimate that the universe contains hundreds of billions of galaxies. Now, the depth of field, going back in time, is from about 2.5 to 10 billion years ago. So that's what this picture is seeing. So this is the Hubble's deep field photograph. As I said, I see it's January 15th, 1996, Bob Williams. So, as I said, to me, it's just one of those pictures. You look at it, you can kind of hardly believe what you're seeing, but there it is. Okay, now let's talk a little bit about stars. So, first of all, stars come in all different kinds, and they have appropriate descriptors. Down here are white dwarfs. Here are type 4 subgiants. Here are giants, bright giants, and so forth and so on. This curve here is what we call the main sequence. You see most of the stars are on that line. Now, what are we plotting here? Well, on the left-hand side is the luminosity or intensity of the light coming from the stars. And of course, across the top is the temperature of the star. So 3,000 degrees Kelvin, that's about 3,000 degrees centigrade, 4,000 degrees Kelvin, 5,000, 6,000. So this little object here, the smiley face, is Earth. Now this picture chart has been made purposely to be Earth-centric. So Earth is purposely at the center of this picture. So the luminosity is defined to be 1, and its temperature is about 5,600 degrees Kelvin, 5,600 degrees centigrade. So there's the smiley face, and these are all of the stars along the main sequence. Now, stars, all of them die eventually. And you'll see why that's true in just a second. So here's a little slide on stellar burning and what happens. So the sun, our sun contains about 99% of the mass of our solar system. And by the way, the universe in general is about 75% hydrogen and about 23% helium. So this star is the same thing. It's 75% hydrogen, 23% helium. Now, the energy that the star emits comes from the fact that the hydrogen and the helium fuse together. So it's a fusion reaction to make heavier elements. Basically, the sun is a gigantic hydrogen bomb sitting up in space, constantly emitting energy. Now, so what happens? Well, this is an enormous object. It weighs about 10 to the 30th kilograms, for those of you who would like to know that. And gravitation is what holds it together. That's the red arrows here. Now, if gravity were the only thing operating, the star would collapse. But these processes that are causing the fusion emit radiation in the form of photons, and they counteract the gravitational force. So the red is pulling in, and blue is pushing out. And as long as there's enough fusion going on, the star will remain stable. But this doesn't go on forever. Our sun will live about 10 billion years, and it will collapse when all of its hydrogen and helium are consumed. Now, we're about 5 billion years along the way, so we've got 5 billion years to go. So you don't have to sell your house just yet, but you might think about it 5 billion years from now. Now, what happens when the star collapses depends on how heavy it is, how big it is. A star like the Earth will collapse most likely to something called a red giant or a white dwarf. If the mass is larger, in the range of, let's say, 3 to 10 solar masses, you could get a neutron star. That's a star that consists entirely of neutrons. If the mass is heavier, 10 solar masses or more, you can get a black hole. Now, the detailed descriptions of all these things is very lengthy and complicated. We clearly don't have time to talk about that tonight. And in fact, all we're going to do from now on really is talk about black holes. Okay, so what is a black hole? A black hole is a star that has collapsed. It's a large mass star, about 10 solar masses, contained in a small volume within something we call an event horizon. So gravitation makes the star collapse because there's no fusion going on to keep that from happening. And it collapses into an extremely small volume. Now, let me give you an example of that. Our sun has a radius of about 700,000 kilometers, 500,000 miles roughly. And it has a radius that size. If it were a black hole, it would have a radius of about 2 miles. So all of that mass gets compressed into something that very extremely small. So then there's now enough mass there, and that the gravitational force is so strong that nothing, and I mean nothing, can escape from it. Not even light. That's why it's called a black hole. Now, you can see them in a certain sense. What do I mean by that? Well, if you're outside the event horizon, stuff can fall into the black hole, and you can see that happening because as it gets toward the black hole, it accelerates and radiates light, and you can see that. But you can't see stuff on the inside trying to get out. And if you had the misfortune of being inside there, you would never, ever leave. It'd be like the Hotel California on steroids. You would never leave. So now there's a lot that we don't know about black holes. In fact, general relativity provides a lot of very descriptive and probably accurate ideas about what's happening in there, but there's a lot not known. So let me just put a question mark there, because just to remind you that you get to the edge, and then you enter an information void. Okay, now last year you may have heard that an enterprising group called the Event Horizon Telescope made an image of a black hole called a galaxy called M87 star. And here's the image that they took. And you see this object in the center here that looks like a black hole. And it is a black hole, but you're not actually seeing the black hole itself. What you are seeing is the shadow of a black hole. Let me just say why. If you imagine this object, it's a sphere on all sides, and it's glowing all the way around. But if you're on one side of it and looking toward the center, toward this thing, you will see a space where it's darker in the middle because the light from the back can't get through. And that's why it looks like there's actually a black hole there. And there is, but you can't see it directly. You're seeing its shadow. Now, the M87 star elliptical galaxy is 55 million light years away and is about 120,000 light years in diameter. So it's quite a bit bigger than our galaxy, and contains trillions of stars. The black hole mass in the center is about 6.5 million solar masses. And it took 8 radio telescopes on Earth looking at this object, and then making a coalescence of their images to create the image that you see. So I mentioned that. I make a big deal of it because what you've really done here is to make a telescope that's the size of the Earth. You've got these radio telescopes all over the planet. They're all looking at the same thing. The telescope, you could argue, is the size of the Earth. And it is. And it's also not the only example of an instrument that's like this, but we won't have time to talk about that. Okay, so let's now talk about what is a gravitational wave. So let's talk about that a little bit.
At the end of their lifetime, massive stars will undergo gravitational collapse, whereby they will be crushed under their own mass into a compact object such as a neutron star or a black hole. Occasionally, these remnant compact objects exist in binary pairs that orbit around each other. This system emits gravitational waves, and over hundreds of millions of years, the system speeds up and the objects get closer together, eventually coalescing in a cataclysmic event that produces a black hole. We believe that the gravitational waves emitted from the coalescence travel away at all directions at the speed of light. The emitted gravitational waves actually compress and expand spacetime as they travel away from the coalescing system. Millions, or even hundreds of millions of years later, the gravitational waves will pass through the LIGO detectors, causing a relative length change of the two arms.
Okay, so let me now show you a schematic diagram of what we just heard. So in the case of the first gravitational wave event that we saw, something called GW 140915, which stands for the 14th of September 2015. So there were two black holes circling each other, one with 29 solar masses, the other 36 solar masses. They're rotating around each other. They're emitting gravitational radiation as they do this. The gravitational radiation causes the system to lose energy, and so it gets smaller as time goes on. And more energy is lost until the black holes are so close that they can actually coalesce and merge. Once they merge, they are like a ringing bell, and they emit energy just as a bell would ring and lose energy and finally become silent. That's what happens to the black hole, the merger. It produces a black hole that has rung down, as we say, and is quiet now. But let's notice here, this final one is 60 solar masses. We started out with 29 plus 36 solar masses. That's 65. So what happens to the other 5 solar masses? Well, they get radiated in space as energy. 5 solar masses of energy, a huge amount. Now, this is the kind of, this is what the radiation looks like, and the gravitational waves as they're emitted. So they're going along here at about, I don't know, about 40, 50 hertz, something like that. And then as the particles get closer together, the wave gets more contracted. And then finally, when they coalesce, the wave is considerably higher frequency, shorter wavelength. And then there's the ring down to a quiet state. Now, the thing that's always just, I can't get over it every time I think about it. On this graph, this is 4/10 of a second. This is 45 hundredths of a second. So this space here is about 2/10 of a second. So in 2/10 of a second, two objects, each weighing over 30, or about 30 solar masses, managed to coalesce and create this black hole in 2/10 of a second. It's just unbelievable to me. But the amount of energy, the time involved, it's incredible. Okay, so what makes gravitational waves? Now, I got to apologize a little bit for this. I don't like this one so well, but it's short, so you don't want to listen to it very long. It's the only one I could find that does a pretty good.
When things move, they create waves. For example, if you shake a stick back and forth in water, you get water waves. Vibrate a piece of metal back and forth really fast, and you get air pressure waves. Shake some electrons back and forth really fast, and you get radio waves. And yes, shake a planet or star back and forth really fast, and you get gravitational waves. Gravitational waves happen because the effects of gravity don't travel outwards at infinite speed. So if the sun were to suddenly jump a few 100,000 kilometers to one side, the changed gravitational field would take time to pulse outwards. And if the sun shook back and forth instead of a single pulse, you'd get continuous gravitational waves. So what's doing the waving? In the case of water, the height of the water.
Okay, so that's a little description of gravitational waves compared to electromagnetic waves, compared to sound waves and water waves. Okay, let's talk a little about history now. So here are two individuals who probably more than any other two people are responsible for proposing that this field could actually exist and then developing the instrumentation to make it happen. So on the right is a gentleman named Joseph Weber. He was born in the United States, but he came here with a Russian family that emigrated from the Soviet Union sometime around 1920 or 1930 or something. And he built a gravitational wave detector that is a cold, what we call a cold bar. It's just a cylinder of aluminum. So those of you who have taken music know very much what a tuning fork is. So this is a tuning fork. It's just an odd shaped tuning fork. It's just a cylinder of aluminum. So it has, like a tuning fork, it has a fundamental frequency, and it also has the harmonics of that fundamental frequency. So it can detect if a gravitational wave came by, it would resonate with one that had the fundamental of this object or harmonics of the fundamental. So it's not a very broadband device. It only is really sensitive at a rather few parts of the frequency spectrum. So that's Joe. On the left is Ray Weiss, who is on the MIT faculty. And he was born in 1932 in Berlin. He and his family made it out just barely in 1938 and came to New York. And then he came to MIT for graduate work and never left. So born in Berlin, almost born in Russia. I'm trying to make a point here that if you need any more evidence about the value of immigrants in this country, you could look at these two gentlemen and be reassured. So Ray's detector is a broadband object. It's LIGO, and it can detect over a range of frequencies starting at about, I don't know, maybe 30 hertz, 30 cycles per second, up to about 5 kilohertz, 5 kilocycles. And it can detect continuously over that wide range. So that's a much more sensitive device, much more broadband device than what Joe Weber was able to create. Joe had he gets a lot of credit in the scientific community, well deserved, for having originated the idea of detecting gravitational waves, which really came from him. But he was very single-minded about what he was doing, and he many times thought he had detected something when in fact he had not. And in fact, his device was not nearly sensitive enough to detect anything. And then, of course, we didn't know that till later. But to me, that doesn't diminish at all from Joe, because that's how science works. You know, you build something, you try it out, it doesn't work, you build something else. That's the way it goes. Okay, so here's what something else is. Here's LIGO. There are two sites, as we learned earlier. There's one in Hanford, Washington, and one in Livingston Parish, Louisiana. So they are 3,000 kilometers apart. If you shine a flashlight here, it would take 10 milliseconds for the light to reach Livingston Parish. And you see on the beautiful landscape here, you see the arms of these two detectors here and here, each one 4 kilometers long, 2.5 miles. So this was funded by the National Science Foundation in 1990. It was constructed by Caltech and MIT in 2 phases, starting in 1994. And the initial LIGO, the first phase, was completed in 2006. And the advanced LIGO was completed in 2015. Now, why did we build it in 2 phases? Well, because people did not believe that this would ever work. And it was incumbent on the project to prove that all of the technology that was needed to make this happen could actually be built. It required advances in a broad range of areas, very intense and stable lasers, a very excellent seismic isolation to insulate it from ground motion, very high vacuum systems, and on and on. And people just didn't believe it, didn't believe it would work. Now, I joined NSF in 1992 as head of the physics division, and so I then became very, very much involved with all this. And I have to tell you, I didn't think it was going to work myself at the beginning. I just thought there was just too many things had to happen right for this to work. But you know, they did. And so we have what we have today, these wonderful instruments. And so the initial LIGO was built. It established the platform on which all the technology could be realized. And then advanced LIGO, which improved on the first one, was completed in 2015. And the first detection was 3 weeks after the completion of advanced LIGO. So a very serendipitous series of events there. So there was ferocious opposition to this project at the beginning on technical grounds that I've already talked about, but also on other grounds. The astronomy community was the leading opponent of this project. Oh, this is a physics experiment. We don't fund physics experiments in the astronomy division. Well, we had a lot of that going on, but we had very strong directors at NSF, and they saw through all of that, and they said, look, this is a paradigm shifter. If it works, it will be a fantastic development, and it's a risk worth taking. Not everything works in science. In fact, a lot of things don't work in science. But when they do, sometimes you get something that's really worth it. So over the lifetime of this project, from 1990 until now, that's 30 years, the project has cost $1.1 billion. That's a lot of money, but 1.1 billion over 30 years, and look at it that way, it's not so much. You think about what we're spending $1 billion on every day here in this country. Well, I don't need to say more. So the LIGO scientific collaboration, which started small, today has over 1,000 engineers, scientists, and students from all over the country. In fact, from all over the world. So it's become quite an amazing thing. Okay, so let's just take a little minute here to see how this works in more detail. So you have here a laser, and this is one detector. So you have a laser, then the light is split into two segments, one going up and down, one going left and right. They're recombined here at the beam splitter, and they come back to the photodetector. And if the arms are precisely aligned, you don't see a signal because they cancel each other out. But if one arm is longer and the other arm is shorter, then you do see a signal because they don't match up anymore. So when a gravitational wave passes, the LIGO arm length differences are 1/1000th the size of a proton. So that's already quite an amazing statement. Okay, so in 2017, the project won the Nobel Prize. And based on this first event, which you've now heard quite a bit about, here are the three gentlemen who were so honored. Barry Barish, Kip Thorne, and Ray Weiss from MIT, Kip and Barry from Caltech. And the statement at the time was it was a discovery that shook the world. And I don't know that even the Nobel Prize Committee realized that there was a sort of a double entendre here. It wasn't just shaking the world in terms of surprise, but also the gravitational waves were really shaking the world, but not by very much. Okay, now let's skip ahead to 2020. That's this year. So black holes are in the news. This year, these three people, Roger Penrose, Reinhard Genzel, and Andrea Ghez, won the Nobel Prize for showing without a doubt that Sagittarius A star at the middle of our galaxy is indeed a black hole, a huge black hole. And that work was done mostly by Professor Genzel and by Andrea Ghez. And Roger Penrose was very important early on for the work he did with Stephen Hawking, proving that black holes were mathematically robust in general relativity. Andrea Ghez is an MIT graduate, and I think she was born in 1965, I think. So she's a youngster. So that's what happened this year. Okay, so I'm going to conclude by just orienting you a little bit more about where we are in space and what all of this means. So this is called the local, I can't make this thing at the top go away. The local galactic group is what it's called. Okay. So here's the Milky Way galaxy right there. And when you look out, you can see some ones that you would recognize, perhaps the large Magellanic and small Magellanic clouds in the southern hemisphere, Ursa Major, Ursa Minor, Draco. All these things are familiar to astronomers. M31, Andromeda, is out here 2.5 million light years from Earth, represented by this yellow arrow. Now, LIGO's initial range of discovery was 50 million light years. You could see something within that space. So that's a hell of a lot farther out than this is. But even so, was not enough sensitivity to really be able to see something. So let's go a little further. So now this is called the VIRGO supercluster of galaxies. Here is this is the VIRGO supercluster here, which includes the ones that we saw earlier on the previous slide. And now this arrow is 1 billion light years. Now all of these clusters you see now are superclusters. They're clusters of galaxies, not just individual galaxies. Now, the event that we saw at LIGO was 1.3 billion light years away. So it was out here somewhere at the edge of this space. And now, unfortunately, LIGO is built in such a way that it doesn't point very well. You can tell it's out there and you can measure the distance pretty accurately, but you can't measure its location on the celestial sphere very well. You don't have enough pointing accuracy with just 2 detectors. So anyway, we don't know exactly where it is, but we know it's out there. Now, advanced LIGO's range is 3 billion light years. So that's take this arrow and multiply by 3 and you're out here somewhere. Okay, so now how many of these do we have around? Well, there's advanced LIGO at Hanford and Livingston. There's an Italian detector called Advanced VIRGO. These 3 detectors are fully operational now, and so there are effectively 3 now working together. And when the 3 are all working and they see the same thing, the pointing accuracy is excellent. There's one being built in India called LIGO India, and there's one now operational in Japan called Kagra. So there's a network of these things. And there's a proposal, well, not yet a proposal, but there's a lot of studying going on about building a super detector, one that's 40 kilometers long instead of only 4. It would be 10 times more sensitive than what we have now. And that, by the way, would be 1,000 times larger volume. It goes like the cube of the range. It could survey the entire universe, and it would be part of an international network. Unfortunately, it'll be done long after I'm around to participate, but my young colleagues will be involved and will be the ones who make it happen. Okay, so just a summary of sort of where we are in terms of cosmology. So amazingly enough, ordinary matter, the stuff that you and I are made of and everything you see around you is made of, is only about 5% of the energy content of the universe. Only 5%. We think that about 27% of it is due to dark matter. Remember that the dark matter is seen in things like galaxies rotating too fast. But the lion's share, 68%, is dark energy, and it's due to the fact that the universe is accelerating. So this is sort of the ultimate misanthropic principle. You remember that Copernicus got into a lot of trouble by pointing out that the sun was probably not the center of the universe, the Earth rather was not the center of the universe, that the sun was the center of our universe, the center of our solar system. That got him into a lot of trouble. So now it's much worse than that. Now, not only is what he said true, but when you look at the universe as a whole, we're only 5% of what's going on. So there's a lot out there that we don't understand, and it's going to be a while until we do. So dark matter and dark energy are very deep enigmas at the frontiers of our understanding of the universe. That's sort of the bottom line. And So this is my last slide. This is Albert. This is the cover of Time magazine in the year 2000. They selected him. When I first saw this, I was astonished that they did it, but I was delighted. Because when you think of all that went on in the 20th century and all the people they might have picked, you know, Winston Churchill, Dwight Eisenhower, you name your favorite good person, they picked Albert because he so fundamentally changed our understanding of the cosmos. So you may know that when Newton died, or just before he died, he was asked, well, you know, tell us a little bit about yourself. And he said, well, if I've seen a little farther than others, it's because I stood on the shoulders of giants. So I submit that we're seeing farther now because of this guy. So that's what I have to say. And thank you very much for listening.
Thank you so much, Dr. Eisenstein. Bob, there are a bunch of questions in the chat, some of which you've already answered. And also, if anyone would like to be unmuted to ask a question in person, just raise your hand or enter something into the chat. So Franklin asks whether you could confirm the claim that our universe contains at least 70 septillion stars, 7 followed by 23 zeros. Astronomers estimate there exist roughly 10,000 stars for each grain of sand on Earth. Is that generally accepted?
I don't know if those specific numbers are generally accepted, but what I can tell you is that in our galaxy, there are hundreds of billions of stars. And so you can draw whatever conclusion you want from that. That's a hell of a big number, but how it translates into grains of sand, I don't know that. I mean, I wouldn't be surprised, but you know, I mean, the numbers are so enormous that it could be.
You answered my question of how do we know how long ago the black holes merged, so I don't have to ask you that. Are there any galaxies without black holes, though?
Well, we don't know, because we're certain. I don't mean to be. I'm not trying to be facetious here when I say this. We obviously haven't measured them all, so we don't know. But the current thinking is that certainly every major galaxy has at its center a massive black hole. That's the current dogma or paradigm, or whatever you want to call it.
Did we get, when I know that after the Big Bang we had this hot, dense, simple stuff that got cooler and more complex as it went, making stars and then galaxies and so on. When
Right.
did we start getting black holes?
Oh, well, some people think that some black holes were generated right at the beginning. They're called primordial black holes. So I give you just a quick elevator speech about that. So the way that would work is when this soup was first generated that you just mentioned, it wasn't perfectly uniform. There were places, there were hot spots and cold spots and dense spots and less dense spots. And the idea is that the dense spots attract other particles because they're larger. And so they make themselves larger. And pretty soon, if you wait long enough, one of those dense spots can become a star. And the star could decay and die. And then that would be a black hole. And that would be a black hole that originated very close to the time of the beginning. So those are called primordial black holes. But no one's ever seen one. And no one's ever seen a signal. The way you would see a signal would be to observe gravitational waves coming from something like that. Exactly what those would look like is not, I don't think that's on firm foundation. To me, it's not on firm foundation yet. So the possibility is open, but I think it's not been confirmed that that's true.
There's a question from Manib Wober. Where is the rest of the energy from a black hole convalesce? It can't all be gravitational waves.
Well, it is actually.
Okay.
I mean, well, let's see. Let me be careful. I mean, in the one we talked about, we started out with 65 solar masses, 29 plus 36, and we ended up with 60. So 60 of it is in the final black hole, and the deficit, the 6 that's missing, is in the form of gravitational waves.
What about quantum tunneling?
Quantum tunneling.
Yeah.
You don't mean tunneling in general relativity. There's also tunneling. Quantum tunneling is a known robust effect in semiconductor physics, which is responsible in part for the reason that transistors work the way they do and diodes work the way they do. But it may be that your questioner means to talk about tunneling wormholes that go from one part of space-time to another, the kind of thing that Kip Thorne talks about a lot.
Something about quantum tunneling by Hawkins.
Yeah, so if it's Hawking, so I see it. So we say that black holes don't radiate. Now I see where he's going. But what Hawking did was to say, well, you know, if you try to take quantum mechanics into effect, you could imagine a scenario at the surface of a black hole where there would be what's called pair production. And so one part of the pair goes into the black hole, and another gets spit out outside the black hole. And that's called Hawking radiation. And that would be evidence of two things. One, that the black hole is actually radiating, which we said before it couldn't. And also it would be an important indication that quantum mechanics plays a role in all this. And people are thinking very actively about that. That was a very important idea that Stephen Hawking had, and it's Hawking radiation has. I don't think I'm wrong about this, but I could be. I don't think Hawking radiation has ever been observed. It's such a small effect that seeing it would I don't think would be really possible. You'd have to look for it in some other way. But now I see what your questioner meant.
Here's a question. Could we chart parts of the universe beyond the light observable sphere by observing its gravitic effect on what we can see?
I don't know, but I don't think so. And the reason why is because gravitation doesn't travel any faster than the speed of light. So it would be limited in the same way that light is.
Paul also asks, what's the meaning of the Earth being at 56,100 degrees K?
Kelvin.
Kelvin.
Kelvin. Well, that's the surface temperature of the sun when you look at it and measure its thermal emission. It's like a black body, and so its temperature, its spectrum, its radiation spectrum, tells us that its temperature, its peak temperature is 5600 degrees Kelvin. If it were heavier, it would have a higher temperature. If it were lighter, it would have a lower temperature.
Sue Reamer asks, is there a book for the educated layperson, a nurse with a PhD in healthcare, on what you have presented, so I could review and digest this marvelous field slowly?
Okay, so the one that comes to mind is one written by Kip Thorne called Time Warps and something, Einstein's Outrageous Legacy. So Andy, I will look up the exact title and I will send it to you, and you can send it to our questioner and give that to him and or her. And then if there are others that I can think of, I can add those to. There's a lot out there now. I got to tell you, it's not all equally worth reading. Let's just put it that way.
Larry suggested a brief history of time. Would you?
So the brief history. So that's written by Stephen Hawking. It's a fine book. Look, nothing that Stephen did was worth ignoring. Should be ignored. But I found that book a little bit on the difficult side, particularly if you're a layperson. Now, maybe the questioner has read it and feels differently about it. That could be. But that book, yeah, I wouldn't. I give it a try. It might work for you.
And Larry also asks, is there any evidence of quantum tunneling from black holes? that we've got yet.
Evidence? No.
Mhm. Nope.
It's the same thing as with the Hawking radiation. That's basically the same idea. And it's not that it isn't there, it's just that we can't see it. It's just so impossibly small. I mean, so what would happen if Hawking radiation is really there? Well, the black hole could conceivably completely evaporate, but it would take the lifetime of the universe for that to happen.
Whatever that is.
Dean has some questions here, 4 of them specifically. 1, are we able to see and measure antimatter in the cosmos? 2, with 100 billion stars in our Milky Way, why are there not more black holes being created from our stars? 3, how did LIGO correlate the chirp with the distant black holes colliding versus another artifact? And 4, would another change in the cosmological constant, like another value or perhaps a function, allow for dark energy? I ask because theories work specific to distance scales, subatomic, quantum to solar to supercluster scale.
Okay, so let's do, I can't remember them all. Let's start with the first one.
Are we able to see and measure antimatter in the cosmos?
Yes, we are. There is a satellite called AMS. I can't remember what AMS stands for, but its purpose in life is to observe antimatter, to go up and try to understand. I don't want to go into too much detail, but at the beginning, there were supposedly equal amounts of matter and antimatter. So when the matter and antimatter collide, they would have annihilated each other and produced pure energy, and there'd be no matter left over. But there is matter left over. That's the stuff we're made of. So the question is there any antimatter left out there? And that's what the AMS satellite is looking for. But I don't think it could see it if it were there, but I don't think it has. But the principle is good.
Antimatter is not like dark matter.
What's that?
Antimatter.
No, it's not like dark matter. No, it's the antithesis of regular matter. It's like, you probably know that there's an electron. The antiparticle of an electron is called a positron, and then the antiparticle of a proton is an antiproton, and so forth. And these things exist. I even did a significant part of my career studying antiprotons at one point. So they definitely can be made right here on Earth.
And his question 2 was, with 100 billion stars in our Milky Way, why aren't there more black holes from ours?
Well, we don't know how many there are. So let's talk a little about how you would estimate that. So if you let's just humor me and say that there are there are 100 billion stars in the Milky Way. So according to that diagram I showed you with the stars versus luminosity and temperature and so forth, you could make a calculation about how many you think are stars that are roughly the size of the sun, or 10 times larger, and you'd get some number. And that number and then you'd have to estimate, well, how many of them are going to decay into a black hole? And you could guess about that. And so in the end, you can make an estimate. And in fact, I looked it up because I thought someone might ask me this. But I looked it up before the talk, and the current estimate is that there's somewhere between 10 million and a billion black holes within our universe, within our galaxy. Somewhere between 10 million and 1 billion, but that's an enormous range. 10 million to a billion, that's a big difference. So far, LIGO has seen 60. You only saw the first one. Now, 60 is a long way from 10 million, but we're working on it.
His third question was, how did LIGO correlate the chirp with the distant black holes colliding versus another source?
Okay, so that's a very good question, because LIGO depends entirely on having a good theoretical understanding of what is happening out there. And that in turn is based on being able to calculate in detail what general relativity says ought to happen. And then, when you do that, you get a series of templates that are candidates for these events. And when you see something that looks, well, what you see in your detector is a burst of energy flowing through it. And then that attracts your attention, and you look at the waveform. And you compare that waveform to these templates, and then you match whatever template seems to fit what you observe. And that's what you take as what you've seen. But you're putting an enormous weight on the theoretical interpretation. It's not as though you're out there looking directly at a black hole. You're looking at signals from a black hole. And those things are close to each other, but they're not exactly the same.
Wow. The fourth one was, would another change in the cosmological constant, like another value or perhaps a function, allow for dark energy? And he asked because theories work specific to distance scales, subatomic, quantum.
No, that's true. But so it's very interesting you asked that because we don't understand anything about dark energy. That he may not realize that that's exactly what people do. They stick in a cosmological constant and they adjust it until they get what they see. But that's not the same thing as understanding. That's a description. It's not an understanding. But it's interesting. The cosmological constant has reemerged from Albert, and it's adjusted to give what we see. But we don't understand where it comes from. And that's a big difference. I mean, it's a fudge. And I'm not, I think everybody would agree with me. I don't think I'm being cynical. I think it's really true.
Well, I think those are all of our questions.
Anybody else have one they want to ask? Okay, Klaus.
Klaus has one. Want to take the mute off, Klaus? Unmute.
The total duration of the signal that LIGO puts out is only, with the way you described that, the intervals there is what, a millisecond or less?
But yeah, it's a few hundred milliseconds. It's a couple tenths of a second. Yeah, so that's for the black holes that I showed you. Now you can have others that are lighter and are rotating in that early phase longer, and you can see the waveform of that for a lot longer time.
I see. Okay.
But the one I showed you, that it only enters the LIGO frequency band for a few tenths of a second. That's true.
Anyone else? Oh, well,
It's a
Bob.
fascinating talk.
it was
There,
indeed.
there was one last question in the chat.
Ah,
Yeah.
do we have an understanding of why the heliosphere can be so much hotter than the surface of the sun?
Yes, we do have an understanding, but I have to tell you, I don't know what it is. The heliosphere is much hotter. It's not just a little bit hotter. It's a lot hotter than what the surface is. And what it is, it's electrons and plasmas boiling off the surface. And I just don't remember right now why it's so much hotter than the surface, but it is. I'll have to, my son is an astronomer. I'll have to ask him. Yeah.
Wow. Well,
If you have time for one more picture, I can show you one more picture, but I don't want to go on too long.
sure.
Okay, so let's go back here. Can you see that?
Not yet.
Oh, what do I have to do? Go back to sharing or something?
Yep.
Yes.
Got to do share screen.
Where do I do that?
And people are saying in the
Bottom
chat,
center.
thank you.
Okay, well, look, we can stop. We don't have to do this.
You can do share screen and just
I
point
just
to.
don't see where it is. That's the problem.
Bottom
Oh, there it is. That's it. Okay.
screen.
Okay, can you see that?
Yes.
Mhm.
Data from the Sloan Digital Sky Survey?
Yep.
Okay, so this is similar to the Hubble picture I showed you at the beginning, but it's 50,000 times larger area. So each one of these little dots is a galaxy. There are 48,741 galaxies in this picture. Now, if you look carefully, look at the yellow ones. Try to separate those from the other colors. You see that they're in filaments and threads, and then there are voids where there are none of them, and then there are clumps where there are several, like here. And if you're good at color discrimination, you could look at the red ones and see the same thing is going on there. And so all of these tendrils and filaments and voids are threads of galaxies. So this is what the Sloan Digital Sky Survey sees. This is 20% of the sky. The Hubble Space Telescope picture that I showed you before was 1/12 the size of the moon. 1/12 the size of the moon. This is 20% of the sky.
5%.
So it's 50,000 times larger. That's why you see so many galaxies here and so few in the Hubble picture. Now you can model this and see how good your understanding is. And then whoever it was who asked the question about how do you take into account dark matter, you can make a model. And you can make an assumption about what dark matter is and what dark energy is. And you can start with a primordial soup of stuff and let it evolve and propagate into what we see today. And this is the picture you get. Now, this is a theoretical model. This is not data. But I find this picture totally enchanting because it doesn't take much of an extrapolation to go from it back to this one, which is real data. And they use this kind of data to tell them what kind of physics goes into making this picture. I like the picture not only because it's just so beautiful, but also it reminds me of neurons in the brain. So maybe the universe is just a gigantic brain. So anyway, so listen, thank you all very much. I enjoyed this a lot, and your questions were very good ones, and I appreciate the invitation a lot.
Thank you very much. And everyone is posting thank yous in the chat window as well.
Well, great. It was nice to meet all of you.
Thank you,
And
Bob.
we will have this recording posted on our YouTube channel eventually, probably. You can
Okay.
go and watch it again if you want to try and scrape a little more understanding off it.
Okay, that'd be great. So would you leave this up a little bit so I can read through these, what people had to say? Because I'd be interested.
Sure.
Certainly.
Are you related to D. Eisenstein?
Yeah, he's my son.
That's what I figured.
Yeah, but I learned everything I know from him and not the other way around.
Yeah.
Very nice to meet all of you.
Dr. Eisenstein, thank you very much. This was fascinating. I have heard wonderful things about you and your son both for years.
Oh, yeah.
My stepfather is Bernie McDonald.
Oh, I see.
And so he has wonderful things to say about you. I'm so glad I got to hear this talk. It's fascinating.
Well, thank you very much. It's nice of you to say that. Appreciate it. Yeah. So Bernie passed away, let's see, 2 years ago now?
No,
I'm thinking of something else. Excuse me. I know I made a mistake. Sorry. Yeah.
okay.
Glad he's still around. Yeah. Okay. Okay, folks. Good night. Thank you all very much. Bye-bye.
Thank you,
Goodbye.
sir.
Bye.
Bye.